Okay, so what was the first question you had?
Can I share my screen?
Yes. Is it allowing you to share a screen or no?
I don't think so. No, it says unknown.
What about now?
Um, no, I can't.
What do you see?
Wait, hold on. Share screen. Oh, it just doesn't let me. It has like the error sign.
Did you press share screen, the green button in the middle?
Yes.
Are you on your laptop?
Yes.
The Zoom?
Yeah.
Um, Wait, send it a screenshot on Discord.
Okay. Where is it? You see it?
Oh yeah, I see. Okay, I'm going to import that picture onto the app and then share my screen. Okay, do you see my screen?
Yeah.
Okay, so the question is saying two resin structures are possible for the anion shown. Do you know what an anion is?
No.
An anion is going to be something that is negatively charged.
Oh, yeah.
Do you know what the name of something that is positively charged?
Cat ion?
Yeah, cation is something that is positive charge. Anion is something that is negatively charged. One resonance form is given, but it is incomplete. Complete the given structure by adding non-bonding electrons and formal charges. Draw the remaining resonance structure, including non-bonding electrons and formal charges. Omit, so that means like don't draw the curved arrows. But we're gonna draw it just to draw the second resonance structure, but don't put that in the homework.
Oh, okay.
So this is an incomplete resonance structure right here. What do you think is missing here? Like what atom do you think is missing something in this resonance structure? Which atom of this whole molecule do you think is missing something?
Um, the oxygen.
Yep, this oxygen is missing something because the question is also asking for adding non-bonding electrons. So like the electrons that are not non-bonding.
Yeah.
Um, the oxygen is missing non-bonding electrons. How many lone pairs of electrons is the oxygen missing?
Two.
Yeah, two lone pairs. So um, to complete it, you should give it two lone pairs of electrons like that,
Okay.
right? And do not to calculate formal charges, like the
Oh, yeah.
negative charge or positive charge. So
Yeah.
what do is look at the number of valence electrons that an atom has, subtract it by the number of electrons it has to itself, and we'll see example problems of that to itself, and that should give you your formal charge, right? There's another equation where you divide it by 2, but I like thinking about like this because it's simpler. So if we look at carbon, how many valence electrons does carbon have? And then a tip to know that is look at the periodic table and see what group it's on. If it's on group 2, it has 2 valence electrons. So what is carbon? How many electrons does carbon have?
4.
4, yeah. So it wants 4 electrons to itself. If I draw out some random structure like this, do you know how to read that bond line structure?
Yes.
Right. Because all the points here are what atom?
Carbon.
Carbon. Right. And then right now, I'm going to say that all of these carbon atoms are neutral. So there's no negative charge, there's no positive charge. How many bonds does carbon want to have to be neutral?
8.
It wants to have 8 electrons to fulfill the octet rule. Right? But how many electrons are in one bond?
6.
There's in one bond there's gonna be 2 electrons.
Oh,
Right?
2.
Yeah, 2 electrons in one bond. So what's 8 divided by 2?
4.
4. Yeah, so carbon wants 4 bonds to be neutral. If we look at this carbon right here, we see it has 2 bonds drawn out, right? But you know how we said it was neutral?
Yeah.
It has 2 invisible bonds. And do you know what the 2 invisible bonds are attached to? What atom?
Hydrogen.
Hydrogen, yeah. So this carbon here has 2 invisible bonds to hydrogen, because we said that carbon wants to have how many bonds to be neutral?
4.
4 bonds, right? Because it wants to have 8 electrons for the octet rule, and each bond has how many electrons?
2.
2 electrons, right? So 2, 4, 6, 8, like that, right? But
Yeah.
we know that this bond is a covalent bond, which is shared, right? So I'm just gonna draw out the carbon like this, and I'm gonna draw out the bond electrons like that. Like there was a bond between those 2 carbons like that. Does that make sense so far? But I'm just drawing out the bonds, the electrons in that bond like this.
Yeah.
Right. One electron of the bond is belonging to that carbon. The other electron of the bond is belonging to that carbon.
Okay.
Right. So this carbon here has 1 electron to itself from this bond. Right. So I'm going to redraw the regular bond line form. This carbon here will have 1, 2, 3, 4 electrons to itself. 4 minus 4 is
0.
0. Right. Let's try something like this then. How many hydrogens are attached to this carbon?
1.
Yeah, 1. Because we see 3 bonds drawn out, 1, 2, 3. So there's gonna be 1 hydrogen like that, right? Let's see if we have something like this carbon here, right? And I draw its hydrogen, and it has a lone pair of electrons, 2 electrons to itself. How many electrons does this carbon have to itself?
To itself.
Yeah. So think of a bond
5.
represented as 5, because a bond will represent like 2 electrons, but one of the electrons of that bond belongs to that carbon, right? It has 1, 2, 3, 4, 5. 5. Those are the 5 electrons that carbon has to itself,
Okay.
right? And then we know that the valence electrons of carbon is 4. 4 minus 5 is
-1.
-1. So this carbon here will have a -1 charge like that, a negative charge like that.
Um.
Right. But let's say we have something like this where there's no hydrogen bond here. If there's no hydrogen bond there and no lone pairs of electrons there, what would be the formal charge of this carbon?
Wait, no hydrogen and no lone pair?
Yeah, no hydrogen, no lone pair. It just has 3 single bonds like this.
Oh, so it'd be like 1?
Yeah, it would be a positive one or negative one.
Positive 1?
Positive one, right? Because it has 4 valence electrons, but it has 3 electrons to itself. 1, 2, 3. 4 minus 3 is positive 1. So
Yeah.
it should have a positive charge like that. Right. So that's the case of carbon. It would be different for nitrogen, oxygen, and the halogens like fluorine, bromine, fluorine, iodine. Right.
Mm-hmm.
And then also if you have a double bond or triple bond, something like this. This oxygen here has 1, 2, 3, 4, 5, 6 electrons to itself. Right. Each bond represents one electron that the atom has, like that.
Yeah.
Okay, so now let's go back to this problem. Now, what do you think is missing here?
Um, one of the carbons with the lone pair, it has a negative
Yep,
one.
negative charge,
Negative one.
like this,
Yeah.
right? And then for resonance structures, always think of moving negative charges. You never move positive charges. So we're gonna move this negative charge over to make a double bond like that, right? Because we said a bond has 2 electrons. When we make a double bond right here, this bond, extra bond, will come from these 2 electrons right here. Does that make sense so far?
Yeah.
Right, but that's gonna be a problem because if we try to make a double bond right here, this carbon here will break the octet rule. It will have a 1, 2, 3, 4, 5 bonds. That's bad,
Yeah.
right? Because that's 10 electrons. That's over like 8 electrons. So to conserve the octet rule, we have to use one of the bonds of this double bond and move it onto that oxygen right there to give that oxygen an extra pair of electrons. Does that make sense so far?
Yeah. So
Right?
the oxygen would have 3 pairs of
Yeah, it would
the,
have 3 pairs of electrons. Yeah. So when I draw that out, it should look like this. 1, 2, 3 pairs of electrons, double bond right here. No more lone pair on this carbon. And now, does this make sense so far on how I drew this structure?
yes,
Right. Now, what would be the charge of this oxygen here? The formal charge.
the formal charge. Oxygen is 6 valence. Mm, -1.
Yep, -1. Because it has 7 electrons to itself. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1. So that oxygen will have a negative charge like that. Let's look
Okay.
at this carbon here. What formal charge should that carbon have?
Um, 0.
0, right? So it's neutral.
Yeah.
Um, whenever you draw resonance structures, all of the resonance structures has to conserve their charge. So that's one way you can check your answers. The overall charge of the structure is -1 charge. When we draw this resonance structure, the overall charge of that resonance structure is also -1 charge.
Wait, but you just changed it from the carbon to the oxygen?
Yep, it just shifted atoms. It moved from
Oh,
the carbon to the oxygen, but the overall structure is -1. But
um,
atom.
oh, okay.
Uh-huh. And which one do you think is major? Which one do you think the negative charge is more happy on? The carbon atom or the oxygen atom? Think of electronegativity. Which atom is more electronegative and can hold the negative charge better?
The oxygen.
Yep, the oxygen. So this will be most likely a type of question. Which one is the major resonance structure? The major resonance structure is the right one. The minor resonance structure is the left one.
Oh, okay.
Right?
So major is like what it's like what they favor?
Yep, the more stable one. Uh-huh.
Okay.
What they favor. Like what it exists more likely on. Right? Now,
Okay.
try putting this as the answer and then let me know if it works.
Okay.
Don't forget the non-bonding electrons, like these pairs of electrons here and here on the oxygen, right? Because it's not there in the original
Okay. Yeah.
problem. Yeah. And also include the negative charges. And then send me the screenshot of the next problem that you want to work on after that.
Okay. Oh, there was a question that asked which one is the major contributor.
Oh yeah, on the same problem here, the same set of
Yeah,
resonances.
they asked right
Okay.
under it.
Uh-huh. Structure B. There's different factors of determining which one is major. This is one of it. Like if there's charges, the charge prefers to be on like the correct atom, like the more stable atom. If it's a negative charge, it prefers to be on the more electronegative atom. If it's a positive charge, it prefers to be on the less electronegative atom.
Wait, can you repeat that? Sorry.
Yeah. Let me give you the list of factors to determine the um major contributor.
Okay.
Right. Factors to consider when determining the major resonance contributor. Right. And then this is going to be like in order of increasing priority. The number one thing that you always have to look out for, the most important factor, is that every atom has to have a complete octet rule, right? Where every atom in the molecule wants to have 8 electrons, except hydrogens. Hydrogens want to have 2 electrons, but every other atom would prefer 8 electrons in organic molecules. The next factor is going to be minimal formal charges. And I'll give you examples of each after this, right? So if a resonance structure has 0 formal charges and then another resonance structure has 2 or 4 formal charges, the resonance structure that is more stable is the one that has the least amount of formal charges, right? Like 0 if possible.
Okay.
Because if you have charges in the structure, that would make the structure less stable, right? You want everything to be neutral,
Okay.
be
So
stable.
whichever is closest to 0?
Yeah, whichever is closest to 0 will be the most stable, or if it's like exactly 0, that's the most stable,
Okay.
right? The other thing is charge placement, which we just did, like which is the example we just did. Charge placement. We want the negative charge on the more electronegative atom, because the more electronegative atom is going to pull that negative charge to itself more. It can hold the negative charge better. Like if we compare that negative charge to a less electronegative atom, that is less stable, because that less electronegative atom does not have a strong pull like the stronger, more electronegative one.
Yeah.
Right? And if we have a positive charge, on the other hand, it's going to be the opposite. The positive charge wants to be on the less electronegative atom.
Mm.
Right? The more electronegative atom does not want the positive charge. It wants the negative charge. Right?
Okay.
Um, the other thing is going to be separation of charges. So if you do have charges, and you have, let's say, a negative charge and a positive charge, do they want to be close to each other, or do they want to be far away from each other?
Far?
Do opposite charges attract or repel each other? Opposite charges?
I forgot.
Yeah. So opposite charges would attract each other. So negative charge wants to be close to positive charges,
Oh, okay.
right? Um, they go towards positive charges. Like charges repel each other. So if you have a negative charge and another negative charge, they are going to be as far away from each other as possible. They want to be as far away from each other as possible. Um,
Okay.
if you have a positive charge and another positive charge, they also want to be as far away from each other as possible, right?
Okay.
But
Yeah.
if you have a negative charge and a positive charge, they want to be as close to each other as possible,
Okay.
right? Um, so I'll give you examples of each in blue. So let's say, uh, let's start. down here and then go up, right? Because the first one could be a little bit tricky.
Okay.
So I'll give you 3 examples of the fourth one here. And another thing is that sometimes when you see practice problems, you will see the atom with a charge, but no non-bonding electrons, like this. If this oxygen has a negative charge, how many non-bonding electrons do you think it will have? Or how many lone pairs of electrons do you think it will have?
Wait, you said if they have a charge, they don't have any?
Uh, so like sometimes if they have a charge like this, they won't show you the electrons.
Oh, okay.
Yeah, but yeah, they expect you to know that.
Oh, so is it 3 pairs?
Yeah, 3 pairs of electrons, um, non-bonding electrons, or 6 non-bonding electrons. But you could also say 3 pairs of non-bonding electrons. You have to be careful of the question, what it's asking for. If it's asking for pairs of electrons, then you would say 3 pairs of non-bonding electrons. If it asks for the number of non-bonding electrons, it would be 6
Okay.
non-bonding electrons, right? But like sometimes they won't draw that out. They expect you to know that,
Yeah.
right? So if I have something like this and say, okay, and then I give you this resonance structure on the bottom. Which resonance structure do you think is major? Which resonance structure do you think is minor?
The major is the bottom one and minor is the top one.
Yep, because the like charges repel each other.
Because they want to be as far away as possible if they're like the same charge.
Yeah, they want to be as far away as possible from each other if they're the same charge. That's right. That's right. Okay, let me give you another one. Okay, which one would be major and which one would be minor for this resonance structure here?
Major is the top one and then minor is the bottom.
Yep, that's right. And how many non-bonding electrons does this nitrogen have?
Non-bonding?
Yeah,
Um, 0,
yeah, 0. That's
right?
right, because it has 5 valence electrons, but it has 4 to itself. 1, 2, and then I'm gonna draw out the hydrogens like this. 3, 4. 5 minus 4, positive 1, which is that positive 1 right there. So we don't want to add any more non-bonding electrons, right? Because if we did, then that would make it go up to 6, making that
Yeah.
negative charge, right? So yeah, this would have 0 non-bonding electrons, 0 lone pairs of electrons as well. Let me give you one more. Okay, I'm going to draw the resonance structure on the right side. Um, okay, this is actually a good one, and I'll show you why. Which one is major? Which one is minor? This
The
is a
left.
little bit tricky one. It looks like the left one, right?
Yeah.
Because the positive charges are as far away as possible, but this is the lowest priority factor. We didn't go over the other factors yet, but we'll come back to this question and then we'll re-answer this question.
Okay.
Okay. Okay. So now let's go over charge placement. We went over this one already. Let me do it again. this one compared to this one, which one is major?
Oh, oxygen, right?
Yeah, the negative charge on the oxygen. Great. Now minimal formal charges. Okay, now I'm gonna go to the second one. Let's say we have this one versus this one. Which one is major for the second factor?
The left one?
Yeah, the left one, because it has less formal charges, zero formal charges, whereas the right one has two formal charges, a negative
Yeah.
charge and a positive charge. But the overall charge is still the same. The net charge is still the same. Net charge of zero, net charge of zero, because the positive one cancels out with the negative one.
Yeah.
Right. Okay. Now let's go over the first one. Let's say we have this one compared to this one. Which one is major? You could basically use the second factor too, but I'm gonna explain the first factor as well.
The right one.
Yep, the right one, because the right one
I
has
less formal charges.
yep, less formal charges, and also every atom has the octet rule. Um, which atom of the first one does not have the octet rule? Does not have 8 electrons.
The carbon
Yep.
and the oxygen.
The oxygen does have 8 electrons.
Oh, because of the lone pairs.
Yeah. And how many lone pairs does this oxygen have if it has a negative charge and a bond that we see right there?
3 pairs.
Yep, 3 pairs like that. So that would be 2, 4, 6, 8 electrons.
Yeah.
That has the octet rule. How many non-bonding electrons or how many lone pairs of electrons does this carbon have?
How many electrons?
Non-bonding electrons.
Non-bonding?
Yeah.
2?
2 like this.
Yeah.
Right. So how many valence electrons does carbon have?
Carbon?
Yeah,
4.
4. How many electrons does this carbon have to itself right here?
5.
5. 4 minus 5 is
-1.
-1, which is not what we want because we have
Yeah.
a positive charge,
Yeah.
right? So 4 minus what? 4 minus x, let's say, is +1.
3?
Yeah, 3. So it wants 3 electrons to itself. So it already has 3 electrons to itself from the bonds right here. 1, 2, 3.
Yeah.
Right? So it has 0 pairs of electrons or 0 non-bonding electrons. Right?
Okay.
How many hydrogens, if any, are attached to this carbon?
Hydrogens?
Yeah.
Wait, it wouldn't show.
Yeah. If there is
Um,
any.
1?
1 hydrogen like this right here.
Yeah.
Right. So if it has 1 hydrogen like that, what would be the formal charge of this carbon?
The formal charge would be 0.
Yeah, 0. But what do we have?
A +1.
Yeah, +1. So there's no hydrogen.
Oh, okay.
Right. Because to have a +1 charge, it needs to have 3 electrons to itself
Yeah.
to get +1. It has 1, 2, 3 right here already. If we add a hydrogen here, then it would have 4, making that neutral. But this carbon is not neutral, so there's no hydrogens there.
Okay.
What about this carbon? How many hydrogens does this carbon have right here?
3?
Yeah, 3 hydrogens. 1, 2, 3, like that, because it's neutral and it has 4 bonding electrons to itself like that, right?
Yeah.
Yeah. So let's go back to that resonance structure right here. This is a tricky one. Use all of these four factors to determine the major resonance contributor. Which one would be the major resonance contributor? The left one or the right one? And think about like the top factor that you have to watch out for.
Okay.
Hey
Okay.
Camilla,
Hi, how's it going?
going well. How are you?
Good, good. Oh,
What days are lectures? Tuesdays and Thursdays for 118C?
yeah, Tuesdays and Thursdays at 7:30 a.m.
7:30 a.m. Oh shoot.
Oh, yeah.
Uh-huh.
When you're done with that, could you go over like carboxylic acid nomenclature?
Oh yeah, the nomenclature. I'll have to review that.
Okay,
I don't have
yours.
like that on top of my head right now, but I can go over like practice like predictive products, mechanisms, synthesis. Right now, but I need to review some nomenclature.
Okay. Or maybe like I guess I forgot a lot, so simple nomenclature.
Simple nomenclature. Okay, okay. Yeah, yeah.
Okay.
I'll find some practice songs for that.
Thank you.
Yeah. Uh-huh.
Is it the right one?
Yeah, it's the right one. Because of what factor? What's the most important factor?
The octet rule?
Yeah, the octet rule. Every atom in the right resonance structure here fulfills the octet rule. What atom in the left resonance structure does not fulfill the octet rule? Oh wait.
The carbon?
Yeah, yeah. This carbon right here.
Yeah.
Yeah, wait, not every atom in this resonance structure fulfills the octet rule because this carbon here does not fulfill the octet rule.
Yeah.
That's a carbocation that has 6 electrons. That doesn't fulfill the octet rule. This carbon here also does not fulfill the octet rule,
Yeah.
right? But this carbon here also does not fulfill the octet rule,
Yeah.
right? But this carbon does fulfill the octet rule. So there's less atoms that does not fulfill the octet rule here, or there's more atoms that fulfill the octet rule here, which is why this is the major one right here, the right one.
Yeah.
Some people might get tricked by the factor 3 and 4, where we said that the negative charge prefers to be at the more electronegative atom, the positive charge prefers to be at the less electronegative atom, and like charges like want to be as far away from each other as possible, right? Because we see here oxygen has a positive charge, which is weird, because oxygen is more electronegative than the carbons, and also the positive charges here are close to each other, so that's also weird. So that
Yeah.
those are tricky things, but the octet rule overpowers those factors. Like the number one thing you look out for is the octet rule.
Okay.
Yeah, and then if all resonance structures has the same octet rule factor, then you look at the other factors. But the first thing you have to look at is the octet rule for
Okay.
this resonance structure major contributor. Right. Okay. Um, Jamila, do you want to go over the nomenclature of the carboxylic acid chapter and derivatives, or like uh like the 118A, 118B nomenclature?
I think a little bit of everything. I'm sure it'll come back, but
Okay. Let's do it.
yeah, sorry about that.
Yeah. No problem. Let me go find how long for that. Let's see. Let's see. Let me Find the problem with nomenclature. Okay. Okay. So please practice with one. Right here. Oh shoot, there's no nomenclature in this one. Let me find another one. Let me see. Last resources. Oh, here. This one. Okay. We'll do version A and version 2. Or version B. Screen. Okay, so what? We'll do the carboxylic acid chapter because that's gonna be midterm 1, and that will have some reveal stuff as well because we need to know like the longest chain, and the smallest substituents as well. So let's see. Wait, what? Did I import the wrong one? Yeah. Yeah. Oh, here, right here. Okay. Okay, so are you familiar with the carboxylic acid derivatives?
No.
Okay, so the parent function of that is like a family of functional groups where the parent function of that like family or derivatives is the carboxylic acid, which is going to be a carbonyl or carbon double bond oxygen that is adjacent to an alcohol. And then this is some random R group, like some random hydrocarbon chain. So this is the parent function, the carboxylic acid right here. Carboxylic acid. And its derivatives are going to be something similar to this carboxylic acid, where the thing that's going to change is this X group right there. Right. So instead of an alcohol, it's going to be some other group. For example, it could be a halogen, where X could be like chlorine or bromine. You might see different names for this. You can see this as an acyl halide, right? But if you have a chlorine, you can say acyl chloride. If you have a bromine, you can say acyl bromide. The other group that you will see is anhydride, where that group is going to be like an acetate group, right? Like a carbonyl with an oxygen like that, with another R group. Like think of it like combining two carboxylic acids together. It kind of looks like two carboxylic acids combining together with no hydrogen right here, right? So that is called an anhydride. The other thing is going to be an ester, right? Where the thing replacing the OH of the carboxylic acid is an OR group. That would be an ester. Right? And then the other thing is going to be an amide. So you are going to see there's three different types that you might see. This primary amide with two hydrogens. You might see secondary amide with one hydrogen and one R group, or you might see a tertiary amide with no hydrogens and two R groups like this. Right? Where the things replacing the OH are these amine groups to make the amide. These are not amines. Like the R groups, like this variable group is an amine, but because it's next to this acyl group or carbonyl group, that makes it an amide. Amide. Right? Just like how we don't consider this an alcohol, because even though this group that I circled here in blue is an alcohol, it's right next to a carbonyl or an acyl group. So the overall structure is considered a carboxylic acid, not just an alcohol, right? Because it's right next to this acyl group or carbonyl group. We have amines here, but because they're next to the acyl group, they are called amides. Okay. So these ones here will be like the highest priority groups in nomenclature. Back in 118A, when we learned about nomenclature and we introduced like alcohol, that had higher priority than other groups that we learned about, like halogens, the smallest constituents like ether, isopropyl, like the hydrocarbon chains, tert-butyl. And then when we went into 118B, it was alkenes, alkynes, and then we went to like the benzenes, like the common names of the benzenes like toluene, phenol, aniline, and then at the end of one to me it was like it was weird. It was like the enamine, enol, enolate. So that did not have too much nomenclature for that. It was more like alkene, alkyne, and the benzene nomenclature. What you can see, the beginning of it is the carboxylic acid and its family members, derivatives, acyl halide, anhydride, ester, and amide, where the difference is going to be this variable group right here. They all have this carbonyl group though. They all have that acyl group, right? So in this nomenclature problem right here, we have amide as the suffix. So that means that we know we have an amide somewhere, right? When you see a big capital N attached to something, then that something is the R group of that N, right? So I'm just going to draw that N out, which is going to represent the N of the amide. This N right here, the nitrogen, is attached to a methyl group, which is a CH3 group, right? So you could draw it out like that, representing that this is the CH3. And then if it's an amide, right, this N is the N of the amide. Let me make that clear. nitrogen of the amide, right? And since it only has one R group, that means that this nitrogen has one hydrogen, right? Because for a nitrogen to be neutral, it wants to have 3 bonds and 1 lone pair of electrons. We see that it already has 2 bonds, 1 to the carbonyl, and I know that this nitrogen is attached to the carbonyl because it's an amide, where an amide is an amine next to a carbonyl. And I know that this nitrogen has a methyl group because of this methyl group attached to it right there. And that's why we see 2 bonds drawn out like that. We have to introduce another bond, which is going to be that bond to hydrogen right there to make it neutral, right? Okay, so this right here is going to be our number 1 atom. Try explaining to me what the rest of the molecule will look like based on the name. But this is like the new material here for the amide part of 118C. But everything else, you could try figuring it out because this is like going to be using the previous material, like 118B and 118A material.
There's like, right, pence is 5 carbons.
2, 3, 4, 5.
And then on the 4th, there's, I don't know what the EN stands for.
In, think of it as alkene. Like, yeah, alkene. So this can be an alkene starting at carbon 4, like that.
Oh, okay.
Right. So this is the overall structure, which is going to be the same thing as this, what the key put, but it's just flipped. Yeah, this is the key, which is the same thing as what we put here, but just flipped like that.
So the ending, the "ene" is the double bond. If it was "eine," it would have been the triple.
Yeah,
And
if it was ine, then it would have been a triple bond, right? Alkyne.
okay. Thank you.
Yeah. Okay. So before we go over this, let's go over some smaller practice problems on this to make it more clear on what's going on here. Let's see. Okay. So for esters, like this, the nomenclature is going to be 2 words. The first word is going to be the R group of the oxygen, right? And it's going to be like a substituent. For example, let's give a very simple ester example. Let's say something like this, right? Whatever is attached to the OR group is going to be the first word of the nomenclature. We see there's 2 carbons attached to that R group, so that's an ethyl group. So the first word of this nomenclature problem is ethyl. Right? The number 1 atom of this nomenclature is going to be the carbonyl carbon, which is always like almost the case if this is the highest priority group. If the ester is the highest priority group, the number 1 carbon is going to be considered the carbonyl carbon. So that's going to be atom 1, 2, 3, 4, 5, 6. The suffix name of the ester is going to be O8. O8, like that. In this case, since we have 6 carbons as the longest chain, it's going to be hexane, not hexene, because we don't have an alkene. We have an ester. So that's going to be hexane O8, like that. Hexane O8.
So the "ane" is for the alkane and O8 for ester.
Yes,
Okay.
that's right. If there was an alkene somewhere, then there would have to be like some kind of number representing whether the alkene is 3, ene, O8. And that would look like this right here.
Okay.
Right. Okay, let me give you 2 or 3 more examples, and then we'll move on to that problem right there. Let's see. And I want you to tell me the number. Oh, wait. Forgot the. There we go. Okay. Try naming this one here and use common names. You could use the full IUPAC name too, but that would take longer. But you could use common names for here. Common names of hydrocarbons.
Butyl, right?
Yep. Butyl.
1, 2, 3, 4, 6. And then hexan,
6.
okay, hexanoate, but there's ethyl on 4 and a butyl on 3.
Right. So I think you counted this as carbon 1, right? This one right here.
Oh yeah, sorry, that's 7. Yep.
Right. Yeah, that's a mistake that I made too. The carbon is 1, which would make this 7, which is hept. Right. Yep. 4 is butyl. Oh, I mean, 4 is ethyl. I mean, 4 is ethyl. And then on 3,
Or methyl ethyl or
methyl.
I forget the,
Uh-huh.
or was it ethyl methyl? I don't remember.
Yeah, so this is if you want to do the full IUPAC name, this is 1, 2, so that's the longest chain of the branch, so that's an ethyl, and then on carbon 1, that's a methyl. So if you want to use the full IUPAC name, you could say 1 methyl ethyl.
Okay.
Or the 1 is optional because there's only one place where the methyl can go to on the ethyl. So you could omit the 1 in this case.
Okay.
But if it was a propyl, then the 1 is required because the methyl could be on carbon 1 or 2.
Okay, gotcha.
But if you want to use the common name, then this would be an isopropyl. Isopropyl. Right. And then we said this was 7 carbon long, so that's heptanoate, like that. Right. Okay. So butyl. Which one do you want to use for the third carbon, the common name or the full IUPAC name?
Oh, I mean, whichever.
Okay. Let's do both just for practice. It might not make a difference. The reason why I'm asking is because we gotta make sure. Yeah, it won't matter anyway because I think E comes before both M and I. So it would be 4 ethyl. Yeah, it doesn't matter which one we use. The order doesn't matter. 1. Okay, the 1 I'm gonna leave it as 1 methyl ethyl heptanoate. Right. And we have to put parentheses here to represent that this is a complex substituent. Complex substituent like that. Right. Or it could be butyl 4 ethyl 3 isopropyl butanoate. No space. There. But there is a space between the first word and the second word here. Yeah, and that's for esters. Ester, amide, anhydride. Yeah, so that's 2 of the derivatives, ester and amide. Tomorrow's office hours, I could prepare some problems for acyl halide and anhydride nomenclature and some more of the other ones as well for review.
Okay, that's Wednesday? Or
Yeah, or for tomorrow's office hours on Tuesday or Wednesday, whichever one you could come by, like whichever one you are available.
oh, you have them 5 days a week?
4 days a week.
Oh,
Monday, Tuesday, Wednesday, Thursday.
oh, okay. I thought it was Monday, Wednesday, Friday. Okay, never mind. Okay,
Yeah,
very cool.
yeah.
Sorry, quick question. You said there's a space between butyl and so for the esters, there will always be a space between the R group and then the main.
Yep. There's always going to be a space between the OR group and the main name.
Okay, and that's just for esters.
Yep, and that's just for esters, right?
Oh,
And for nitrogens, they will have the big N as part of the name if there's an R group attached to that nitrogen of the amide. Right? If you see an amide that has two R groups, like let me say something like this, you might see it like this: N ethyl, N methyl, and then whatever that whole thing is, which is this is carbon 1, carbon 2. That's ethanamide. Right? Or if the N has the same R group, like let's say two ethyl groups, like that. You know how back in the 118A nomenclature, when a carbon has two of the same constituents, we said like 3,3 diethyl. Like we use the number 2 times, and then we use di, whatever the thing is, ethyl propyl,
Yeah.
represent that. This is gonna be N. It's like the numbering system, but N is its own special number, or like special thing. Right?
Okay.
NN dash diethyl, and then let's make this a little bit different. 1, 2, 3, 4. 3 methyl. Oh, let's make this a little bit more interesting. Let's make that ethyl, but I have to make this longer. Okay, I want you to name this for me. Wait, let me okay, there you go.
Wait, but this one doesn't have a double N, right? Because it's only one. It's
This one here, it has two R groups. Which are these two R groups here?
So N, I'm so sorry.
Yep, N, right? Because that's going to represent the two R groups of the on the nitrogen. But where is the other ethyl group? We have one ethyl group here, another ethyl group here.
Oh, on 3.
On 3, so it'll be NN3
Ethyl.
tri.
Oh, sorry.
Triethyl, right?
Hepta something.
Heptanamide.
Heptanamide. Okay, gotcha.
Right. Yeah. If that ethyl wasn't there on carbon 3, then it would have just been NN dimethyl.
Oh, okay.
Heptanamide.
Okay.
But if let's say on carbon 3 it was a methyl group, there would be NN dimethyl 3-methyl heptanamide. Right. You have to keep track of the substituents, and if they're the same, group them into like a list, like NN3 or 234 or 233, and then remember the prefix di, tri, tetra, and so on and so forth.
Okay.
Yeah, we'll do more practice on this tomorrow if you can come, or on Wednesday if you can come that day.
Okay. I'll try to come tomorrow.
Okay. Yeah, and you can also text me like ahead of time what you want to go over, so I could prepare
Oh my
practice
gosh.
ahead of time
Thank
too.
you so much.
Yeah, no problem.
Thank you. I'll see you tomorrow.
Yeah, see you tomorrow, Camilla.
Bye.
Bye.